Good morning, guys. Today we're going to talk about reaction mechanisms. Mechanisms are the way that a chemical reaction proceeds. And to introduce this idea, I want to talk about photosynthesis. Photosynthesis is a well-known chemical reaction, and you probably remember it from biology class. And the idea is that you have some carbon dioxide and some water, and that's all you need to get some sugar molecules. Oops, C6. H12O6, and some oxygen as well. Six of these, one of those and six of these, right? So that's the photosynthesis reaction. And based on what we were talking about yesterday in collision theory, you might think maybe all we need is to get 6 carbon dioxide molecules and 6 water molecules and get them all to collide all at once, and that'll give us some sugar and some oxygen. Now, in theory, that's possible, but it's extremely unlikely. Having 12 molecules all collide together at once to form exactly what you wanted is very, very improbable. It's not likely to happen. And in fact, we know that photosynthesis does not occur in one step. It occurs in a series of steps, which are referred to as the reaction mechanism. So we're going to learn about mechanisms today. It's how reactions occur over a series of steps. And there is a connection with the rate law and kinetics that we've been talking about over the past week and a half. So reaction mechanisms. Most chemical reactions occur by a series of steps known as the reaction mechanism. What's neat about studying kinetics is that it can in fact allow us to gain insight into how a reaction may actually be occurring. So there is a connection between kinetics and the mechanism of a reaction. The rate of the reaction and its mechanism, how it happens, are intimately connected. Okay, so let's consider the following reaction. I'm going to let carbon atoms be some black atoms, and nitrogen's going to be blue, and oxygen is going to be red. And let's draw this out here. So we've got a nitrogen dioxide, so that's 1 blue and 2 reds. I'm not going to worry so much about what the molecules themselves really look like, whether they're linear or bent or whatever. I'm just going to stick the atoms onto each other. Carbon monoxide, so 1 black, 1 red. Okay, and when this reaction occurs, you end up getting nitrogen monoxide, and I'm going to keep the oxygen on the left so it looks kind of similar to this one, and carbon dioxide. So if you look and you see what's really happening, it doesn't look that complicated. You got these 2 molecules, and it looks like all that's happening is one of the oxygen atoms right there, highlighted in yellow, is getting passed off to the other thing, and now it's on the other molecule. Okay, so it doesn't look like a terribly difficult reaction to imagine happening. Even in collision theory, we can imagine the nitrogen dioxide and the carbon monoxide hitting each other, passing off one of the oxygen atoms, and you get these new bonds to form. Okay, but in studying the kinetics of this reaction, we know that it is not a one-step reaction. Okay, there's really, really, really good evidence that it can't be a one-step reaction. Even though this reaction seems straightforward, the oxygen atoms getting transferred, it turns out what's actually occurring behind the scenes in the mechanism is more complex. Okay, the equation above just shows the net results of the mechanism, if you will. So this right here, it's kind of like our photosynthesis reaction up here. Photosynthesis does not occur just in one step, but when we write out the reaction equation, that's what we're that's the overall result of photosynthesis, of course. Okay, so if you get some plants and you know, give them some water, you can actually measure this overall type of thing occurring in a closed system. You would see less and less carbon dioxide in the air around the plant and more oxygen around the air. So we know that's the overall type of thing, and more sugars in the plant cells. But just like this is not occurring in one step, this one doesn't either. So the rate law for this reaction is known by experiment to be, this is the differential rate law, K, the rate constant, concentration of NO2 squared. So some scientists have done some rate law experiments. It might have been with the method of initial rates. It might have just been measurements of concentration versus time. And it's well established that this particular reaction has this rate law. Okay? And what's interesting is, even though, if you look at the two reactants up here, those are our reactants, even though, you know, you might be curious, like, shouldn't we have written out the rate law, you know, before understanding what the orders of reactants were? You know, we would have probably assumed that carbon monoxide is playing some type of role here, but apparently it's a 0th order reactant. Carbon monoxide is not playing any role in the overall rate. So one of the reactants doesn't seem to be that important for the rate. Carbon monoxide concentration, I should say, does not affect the rate of reaction. So it's a 0th order reactant. And so we don't even really include it in the rate law, right? That term right there would just be equal to 1, so we don't include it. So we know, scientists know that that's the rate law. So what does this have to do with the mechanism? This allows scientists to propose a mechanism. The mechanism has to be consistent with what we know about the kinetics of the reaction. And so scientists believe that the reaction proceeds by 2 elementary steps. I want you to underline elementary steps. Elementary steps show us molecules that are colliding, molecules that actually are colliding, okay, for that particular step to proceed. These are the things that actually have to come into contact. Okay, so they believe the first step is that 2 nitrogen dioxide molecules collide with one another, and that generates something called an intermediate, NO3. They think just for a moment there's a little bit of this NO3 stuff, and some NO is generated as well. And this reaction has its own rate constant. So this elementary step has its own rate constant. Okay, so K1. And then there's a second step in this supposed mechanism. This NO3 goes on to react with the carbon monoxide that's present. And that generates some NO2 and the CO2. That step has its own rate constant. Okay, so there's something that's being generated in the first step that is immediately consumed in the second step, and that is what we call the intermediate. NO3 is the intermediate. Okay, it's something that gets generated, but then it is consumed later on. It doesn't accumulate. Okay, the reactants, they're ultimately getting turned into products, but this is a product that reacts, and so it doesn't accumulate like the actual overall products do. Okay, so it doesn't accumulate. Okay, so like the products in the overall reaction will. Okay? Now, I just mentioned this about elementary steps, so I got a little bit ahead of myself. An elementary step is a reaction whose rate law can be determined and written according to its molecularity. There's a new word for you, molecularity. Molecularity is the number of molecules that must collide to produce the reaction in that step. Okay, so elementary steps show us the number of molecules and the actual molecules that are colliding for that step to occur. And their rate law can be inferred from the molecularity, that number of molecules. So for instance, in step 1, 2 molecules have to collide here. So that has a molecularity of 2. That's called bimolecular, right? And so this step 2 is also a bimolecular step. Unimolecular steps involves 1 molecule. Bimolecular, termolecular involve the collision of 2 or 3 molecules respectively. You might be wondering, how in the world can there be a unimolecular step? How is 1 molecule going to collide with itself? Normally it doesn't. You might put in a little bit of energy with some sunlight or something and it causes the chemical bonds to break apart. That would be like a unimolecular step. It's not really a collision, but there's just 1 molecule involved there. Okay, so we have 2 bimolecular steps that make up the mechanism of this reaction. Okay, so here's why scientists believe that this is happening. The overall rate law is known by experiment to be second order nitrogen dioxide. Now here in the mechanism, there is a step with that particular molecularity. In step 1, 2 nitrogen dioxides are colliding. And if it's actually an elementary step, we can infer its rate law by its molecularity. Since 2 of these are colliding, it has an amplified effect. Concentration has an amplified effect on how quickly the rate's going to occur. And so this step here corresponds to the rate law. Now, apparently, this second step must be much faster. Okay, this step right here, if we assume that this step here is a slow step, and step 2 here is a very fast step, much faster. So step 1 is slow, step 2 is much faster. Which one of these steps would contribute to the overall rate law for the reaction? It's going to be the first step, the slower step. The slowest step of a mechanism is called the rate determining step. The rate determining step. I want to give you an analogy or just another example for a rate determining step. Let's say you have a series of funnels that can accommodate various amounts of water, various flows of water. Okay, so let's say that you have a funnel here whose maximum capacity is 10 milliliters per second. Okay, so if you're familiar with a funnel, you know, if you pour in just a little trickle of water, it has no problem draining out, right? But if you start pouring in lots and lots and lots and lots of water, you might surpass the capacity of this funnel to drain as quickly as it's being filled, and so eventually the water starts filling up, and if you don't slow down how much you're pouring in there, it's going to overflow, right? But let's say this funnel is able to release 10 milliliters every second, so that's like its capacity. Okay, so it's able to handle that. And so let's say it's at its capacity. So we're putting in the perfect amount of water so that we never really overwhelm this funnel. Okay, so it's just draining out. All right, but let's say we've got another funnel here beneath. There's a really ugly looking funnel. Let's say that funnel has a capacity of 7 milliliters per second. And then, so the water's draining through here. And then we've got a third funnel. And this funnel is able to accommodate 8 milliliters per second. Okay? What is going to be the rate of flow out the bottom of these three funnels? Okay, so let's imagine we're putting water in here at 10 milliliters a second. It's the perfect amount for this first funnel. So here it's still 10 milliliters per second. As it goes into the second funnel, the best that that funnel can do is 7 milliliters per second. Okay, so here we're down to 7 milliliters per second. Now let's ignore for the moment that that funnel is going to get like, you know, it's going to overflow or something. 7 milliliters per second. Okay, now that 7 milliliters per second enters the third funnel, which could deal with even a faster rate, 8 milliliters per second. Does that mean this is going to exit at 8 milliliters per second? No, because it only went in at 7 milliliters per second. So after going through these three funnels, we are down to the speed of the slowest funnel. Okay, so the second funnel here would be the rate determining step. I don't know what I just wrote there, but you get the idea. Rate determining step. Okay, and it's the same with chemical reactions. If we have a series of steps and let's say one step is much slower than the other steps, that slow step, whether it's the first one or the last one or somewhere in the middle, the slowest step will be the rate determining step for the entire mechanism. Okay, so going back to our mechanism over here, we know that the overall rate law is second order nitrogen dioxide. And here we have a slow step, the slowest step of the mechanism. It's supposed to be the slowest step because its molecularity is nitrogen dioxide colliding with nitrogen dioxide, which would give rise to this overall rate law. Plus we know carbon monoxide has no role whatsoever in the overall rate. And so the carbon monoxide doesn't show up until the fast step. Okay, so we have a step whose molecularity matches or accords with the known overall rate law, and a mechanism which adds up to the overall reaction. Okay, do you remember Hess's law? Of course you do. These mechanisms are composed of steps that add up to the overall reaction. So let's just confirm that over here off to the side. A mechanism should add up. The reactions in the mechanism, those elementary steps, should add up to the overall reaction. Oops, sorry, NO. Okay, so that's step one. Step two. Remember, that's the slow step, the rate determining step. This is the fast step. Okay, and then we get some NO2 and some CO2. Let's add these together and see what we get. All right, here's all of the reactants. Here's all of the products, but do you see some things on each side that would cancel? One of the nitrogen dioxides cancels. The nitrogen trioxide cancels out. And here are the reactants and products that are left over. NO2 plus CO yields NO plus CO2. It's the exact same, that's overall. It's the exact same as the reaction that we're studying. Okay, so those are some steps that add up to the overall reaction. Now, what's the rate of this overall reaction? It's the rate of the slowest step whose molecularity matches what we know to be the rate law. Okay, so we've got a step that corresponds with the known rate law, and the individual steps add up to the overall reaction. So this is a valid mechanism for those two reasons. Okay. Now in the past, mechanisms were proposed. Sometimes you couldn't really be sure whether or not the mechanism was actually the way the chemical reaction occurs. Okay, because molecules, you couldn't see them. Is this actually what's happening? But it's valid. It's valid to think that this might be how it's happening, because we have a slow step whose molecularity accords, that means it's in agreement with, the known rate law. I don't know why that letter S is stuck there. That's bizarre. Anyway, so it accords with the known rate law that's experimentally determined, and the steps add up to the overall, there, they add up to the overall mechanism. That's a really weird bug here. Here. There we go. Okay, so for those two reasons, it's a valid mechanism. Let's continue on a little bit further. Let's talk about how elementary steps give rise to particular molarities and what the overall rate laws would be. Let's get through this page quickly and define some terms and then be done. Okay, so this is a unimolecular step here. Talked about those just a second ago. These both here are bimolecular, two different cases for bimolecular. You could have two of the same species or two different species. Okay, so A plus A colliding or A and B colliding. At any rate, those are bimolecular. And then several cases down here for trimolecular. Maybe you need two A's and a B. Those are termolecular, excuse me. Termolecular. Not a word I use every day. Termolecular. Or perhaps you need three different species. These here, guys, this is very rare. That rarely happens. And because it's just very, very improbable for three species all to hit at the same time with the right orientation. So these are not very common, but you know, they're possible. So normally people don't propose termolecular steps and reaction mechanisms unless they have really, really good experimental evidence to do that. Okay, so termolecular, and then beyond that, gosh, 4, 5, 6 molecules, 12 molecules, like in photosynthesis, there's no way. There's no way that that's how those reactions occur. Okay. So what would the rate laws be based on the molecularities here? Okay, the rate law here would be, rate equals K A raised to the first power. Here, rate K A squared. This one, rate K A to the first power, B to the first power. Here, in the termolecular steps, rate K A, can you guess it? How many A's over here? Squared. B to the first power. And down here, rate K A to the first power, B concentration to the first power, C concentration to the first power. Okay? Now you might remember before spring break we were talking about how for rate laws they have to be determined experimentally. You cannot simply look at a chemical reaction and try to determine what the rate law is going to be based off of the coefficients. So, you know, it's not possible, for instance, for us to look at photosynthesis and then just suddenly decide, oh, there's a 6 here and a 6 here, so therefore the rate law must be CO2 raised to the 6th power, H2O raised to the 6th power. Okay? We can't do that unless it actually is an elementary step. But we know, we have really good evidence that this is not an elementary step. Okay, so since it's not an elementary step, that's why we can't write the rate law based off of the coefficients. Okay? But if it is an elementary step, then it actually is the molecules that need to collide. And because of that, we actually can write their rate laws based off of their molecularities. The reason for that is fairly simple. I think the best one to explain, the easiest one for me to think through is this one. Why would the rate law be first power A and first power B? Well, if these are actually the species that need to collide, A and B, right? So let's, I'm going to have the A be red and the B be yellow. If you actually have some A and B, there's some A, and then the B is yellow, that need to collide. Okay, if there's only a small amount of B in there, then the possibility for effective collisions is maybe not so good. But if we can increase the concentration of B, now we're increasing the probability for effective collisions. The more B, the higher the probability for effective collisions. So, and in fact, if we double B, we're going to double the chance for effective collisions. If we double A, we're going to double the chance for effective collisions. Okay? So A and B are both important contributors for the overall rate. And so that's why their rate law would be A and B concentration. All right. Now, you can kind of apply the logic there to the other types of elementary steps. But this one's the easiest one for me to understand anyway, right? If it's A and B that have to collide, if I can increase the concentration of either one, I'm going to increase the rate of the overall reaction. So they're both first order for the rate law. Okay, final little bit here for today. Can you define elementary step and intermediate? We did it earlier. Okay, I want you to write those out on your own. What is an elementary step? What is an intermediate? Let me tell you about catalysts right now. Okay? In the other video, we talked about a heterogeneous catalyst. Okay? And so that's like often a solid material. Okay? Where the reactants can accumulate. And that helps the reaction go faster. But I want you to know about homogeneous catalysts as well. A homogeneous catalyst actually looks like a reactant, but it gets regenerated as a product later on. And so it reacts like the reactants do, but then gets regenerated. Later on. And so it never, its concentration remains constant. Okay, so its concentration doesn't really change at all throughout the course of the reaction. So reactants concentrations are dropping, but a homogeneous catalyst, its concentration remains constant over time. And it's sort of like, it looks like an intermediate. Let me give you 2 examples of these and then we'll be done for real. An intermediate would be like if you have A plus B yields C and D, and then C plus B yields A and D. There is, maybe that's the mechanism. What would the overall reaction be? C is an intermediate. It gets generated in the first step, but then gets used up in the second step. And so the overall reaction does not include C at all, right? It would be A plus 2B yields A, sorry, the overall reaction would be 2B yields 2D. Okay? Because notice the C's would kind of cancel out. C is our intermediate. Okay? But A is something else. A is a catalyst. Okay, it's that homogeneous catalyst. It's necessary for the reaction to occur, but it doesn't seem to really be reacting away. Okay, so let's leave it there for today.